So good afternoon, everyone. My name is Shehab Eldeen Ayman, and today I'm presenting my paper on depth-based region proposal for its robust two-stage real-time object detection. This is in partial fulfillment for my master's degree at the British University in Egypt. So let's start. So the agenda for today, we'll start with the background and object detection. We'll go through some literature survey, the limitations of said literature, the proposed solution, and results and discussions. So the background. So modern object detection techniques have been evolving at a rapid rate. So in early days, it was quite difficult to perform what we call real-time object detection, right? But now it's completely possible. At the early days, the competition between object detection algorithms was measured in terms of the number of classes they could identify and the level of their accuracy. So it was only comparing how many classes an object detection algorithm can classify. State-of-the-art techniques are trying to seek a balance between speed and accuracy as technology, as computer vision technology is taking part into our every day-to-day life, right? Okay, so a bit of a background. So what is object detection? Object detection is basically allowing us to identify and locate objects in the scene. So here we're talking about scenarios where the scene is not occupied mostly by a single object, but it is many objects occupy a scene. These objects can be of the same class or multiple classes. They can, of course, overlap or partially occlude, and there can exist multiple instances of the same class in a scene. So what an object detection algorithm should do is identify these objects in the scene, locate these objects, and of course, identify which classes they belong to. So looking at literature, we can see that mostly, and here we're talking about deep learning approaches to object detection, we can see that they are divided into two-stage models, or what we call multi-stage models, and one-stage model. And the difference is the two-stage model, from its name, it uses multiple stages to detect objects in the scene. So the first stage is called region proposal, which relies on region proposal algorithms to find potential spaces in the scene where there might rely on objects. So here we haven't detected the objects yet, we're just guessing or predicting where the object might be in the scene. And there are different techniques to do region proposals, for example, sliding window and some other techniques. It is slow to run, but it has higher accuracy because we can make multiple runs on each frame just to find the objects. And the most famous examples in literature are RCNN, fast RCNN, and mask RCNN. For one-stage models, what they did is that they combined the region proposal algorithms, so the step or the process of finding potential objects in the scene, it has been combined with the object detection itself into a single pipeline. So what happens is a deep learning algorithm passes on a frame one single time per frame, and it tries to find the potential locations of the objects, and it also identifies the labels of the objects or which classes they belong to. So thinking about it, since we're doing one run per frame, so it's quite fast compared to two-stage or multi-stage models, but it has the downside of being lower accuracy compared to the two-stage model due to that compromise. And of course, the most famous of these approaches are YOLO with all its different versions, and SSD, which is single shot detection algorithm. So looking at the literature, and keep in mind we're aiming for real-time object detection. So the obvious limitations are the compromise, the always compromise between accuracy and speed, and that 2D input frames, so we're talking about regular RGB frames or even grayscale frames, they lack the accurate representation of locations of objects in the scene. And what I mean by that is, if we look back at the photo of the dog, the bicycle, and the car, here this was ran on YOLO Of course, YOLO was able to detect the objects in the scene and localize them correctly with a relatively high degree of accuracy, but it cannot really infer that the car is in the background and that the dog is in front of the bicycle, occluding part of the bicycle. So there's a bit of a missing understanding to where objects actually reside in the scene. So we need to look at this Z factor or the depth factor. Looking at the X and Y and drawing the bounding boxes is not really enough in some select applications. And looking at select applications, there are many times where it's a waste of computational resources in trying to determine objects or detecting objects in the scene. Here you can see this example of a photo. This is recorded using the dash cam in my car, actually, back on the road on a gray sky day. So we can see that the sky occupies around 57% of the frame, while the road covers 17%. And in this scenario, because it was in a relatively empty street, we only had one visible car in the horizon, and it occupied less than 1% of the scene. So thinking about traditional region proposal algorithms, it would waste many computational resources just trying to find or guess or pass over the frame, trying to find potential objects that we want to detect. Even though if we do a pass on 1% of the frame, we can find the single object we actually need to detect, right? So looking at another limitation is some difficulty in identifying based on the deep learning algorithm. There might be some difficulties in identifying overlapping objects, and this of course happens whether objects are of the same class or of different classes. So we're talking about a dog occluding a dog, or in this case, a dog occluding a bicycle. So what happens, or to mitigate that, is the workaround is to increase the number of bounding boxes and decrease their sizes in order to find these objects. But this results in a big computational penalty where you need to identify, even if you're doing this over one single run over a frame, you have so many small boxes, which means you have to try to guess if there is an object in each single box of these or not. So even doing 100,000 boxes per frame, that's 100,000 guess, that's 100,000 classifying try, which is a lot of computational resources, which is potentially wasted. Another limitation, and this was actually highlighted in literature by a paper by Ravi, when he tried to detect lizards in the frame. Here we can see that using aerial footage of the desert, we can see that the lizards are so small they occupy minute parts of the image. So we're talking about, of course, again, less than 1%. We can see that detecting those kinds of lizards in a real-time application using the traditional deep learning algorithms was almost quite impossible, according to his paper. So how do we solve that? What is my proposed solution? So my proposed solution is to develop this modular pipeline that captures depth information alongside 2D frames. So we add depths to our understanding of the scene. We create a multi-stage real-time object detection pipeline. So our proposal here is creating a 2D, a two-stage or even a multi-stage pipeline that utilizes depths for region proposal. So what this allows us to do is it allows us to sort and prioritize object detection based on distance. So why some would ask, why would we need to sort or prioritize objects based on distance? Here we can go back to the image of the dashcam footage. In case that we are very limited on computational resources and we cannot make a single run over a frame due to the high resolution of the frame or the limited computational power we have, we can prioritize objects that are nearer to be detected first or identified first versus the objects that are further, because the objects that are nearer propose much more importance in some scenarios to the objects that are further. In case of autonomous driving, we are more likely to hit an object that is nearer than an object that is further, right? So that's why we focus on the nearer objects first. But then, of course, all the objects in the frame get detected, right? Okay. So we sort and prioritize objects based on distance, and then we generalize this developed technique through modularity. So the system is based on multiple modules. Each of this module can be interchanged or swapped for another module for the ease of improvement and incrementation over the system. So the two main modules are the neural network model and the depth sensor. And the modularity here was invaluable during the development of this pipeline, because at any given point in time, we can swap the depth sensor we have, whether we have indoor infrared short range sensors or outdoor LiDAR long range sensors. We can swap the sensors without having to modify anything related to the neural network core. Same thing that we did when we were experimenting with multiple neural network cores. So those were multiple neural network classifiers. We could change those. We can change the training set or the training data without having to modify anything related to the depth sensing model. So looking at the figure, what we do is that the depth sensor produces, so the depth sensor here is alongside a regular RGB camera. So the RGB camera captures the RGB frame, and the depth sensors capture a depth frame, and those are mapped onto each other to present the frame in 2D with distance information, and then it is fed to the neural network. Objects that are extracted from the depth data are fed to the neural network classifier to produce a label. So looking at the depth acquisition, we stumbled upon a hurdle of when using or when experimenting with multiple depth sensors, is that we didn't find a universal way of representing depth, or a universal format to say for representing depth. So looking at regular 2D images, you can always think of raw format, JPEG, JPEG. You can always think of those standard and widely compatible formats. But for depths, we didn't find this widely popular or this unanimous compatible format without proprietary applications. So what we did is that when we captured the depth information, we presented it as a grayscale image, where the color intensity indicates the distance from the sensor. So what we did is that we made the closest objects to the sensor have the highest intensity values, so those are the ones closer to whites, and the further objects tended to have a darker or a lower intensity pixel value. And of course, this mapping was changed based on the operational distance of each sensor. So for example, from the infrared of the Kinect operating at a 2-meter maximum compared to a LiDAR sensor that operated on 1.5 kilometers, the grayscale intensities were remapped based on the operating distance. The produced grayscale image, the depth image, is then mapped onto the RGB image, and a basic layer extraction breaks down the depth map into multiple operating distances, sub-distances based on the threshold that we provided. So by this, we create multiple layers, or we divide our image into multiple layers, and each layer represents this operating distance that we can then feed a classifier to identify objects. For the neural network core, tested a lot of predefined neural, but we settled on VGG16 and ResNet 50 because they provided a quite good balance between accuracy and performance. VGG16 and even 19 later showed better accuracy, but it took much longer processing time compared to ResNet, which showed good performance actually, but was less accurate than VGG16. And here, coming back to the modularity of the system based on the computational resources on hand, whether this is deployed in a mobile scenario or deployed in a server space, we can always swap the neural network core for something that is more accurate and stronger if we have the computational capacity to do so. For the results, we chose to train on a standard data set in order to compare it to other neural networks at that time. So we settled on Pascal VOC 07. And if you think about it, so where is the depth part, the depth information capturing and training? And this is where the modularity also comes in, is that the depth information is not really needed for training the neural network, because the neural network, we didn't want to modify it to keep each operating module standard. So this means that the neural network core is a regular neural network that accepts RGB image without any depth information, because it is used just to train on the objects themselves, right? But the part of capturing where the objects are in the scene, this is where the depth information comes in. So we do not need to add this in the training loop. The accuracy metrics, the accuracy we measured was over the mean average precision, and it was measured at a minimum of 0.5 intersection over union rate, and the time measured was milliseconds. So the testing for this pipeline was designed inherently to run on a very average computer. So the test we conducted here was ran on a quad-core i5 from back in 2015 and a regular GTX 1060 with only 6 gigabytes of frame buffer. So we used a regular computer, a very attainable computer, just to test if it's possible to migrate this pipeline or this system to work on smaller, more mobile and less power hungry devices, for example, used in autonomous driving or whatnot. So using ResNet, looking at the milliseconds, so the time taken to detect the frames, we could see that ResNet did it over around 86 milliseconds, which is half the time needed, or even less than half the time needed by VGC 16, and considerably less than 50 neck and neck with YOLO v3, because we tested with YOLO v3. But then again, the main advantage would be when we have other detection networks that are as fast as our implementation is in accuracy. So looking at the accuracy, looking at the mean average precision, we could see that VGG, of course, beat the ResNet module in accuracy, but both of them were higher than SSD, both of them were higher than MobileNet, which is supposed to be very efficient, so we scored higher accuracy than that, and higher than ResNet 50 V2. So yeah, and slightly, if based on our testing, VGG was actually slightly more accurate than YOLO v3. So those are our results, and this was another scenario that we captured using the dash cam. Here we had a lot of overlapping objects, of course, from the same class, because this is the road and these are our cars, but our system was able to identify each object quite easily, actually, and in a relatively timely manner. So that's my presentation. Thank you very much for having me. And if you have any questions, feel free to ask.